I am Professor Khanna from IIT Bombay, and I am a professor in the Materials and Metallurgy Department of IIT Bombay. And we have various groups, and one of the groups which I am heading and controlling works on smart materials or smart coatings. I mean, you can call it as a material. Ultimately, whatever you modify and it shows smartness, so finally it is a smart material. But basically, we are trying to modify materials on the surfaces to bring some kind of a specific function. And in today's talk, I'm going to give a brief introduction about the work which we are working on self-cleaning coatings. And this kind of functionality has such a strong application today in various fields. I mean, you talk about solar technology, you talk about the new buildings which are made of glass and so many things, furnitures at home, and many things like that. And although the subject of self-cleaning is not very new, people are working for a very long time, but a systematic study to understand the thing and also create a formulation or coating which can give the understanding as well as its application to the industry. That's what we thought is the way this work was planned. I was especially asked to cover the inorganic-organic hybrid-based things. And what are these? I will just introduce in that. So, as I have already told, a smart coating is that which, in general, we know that more than 85% of materials which are used in several industrial or even household applications are somehow protected. And protection is done by simple paint coating, galvanization, high-class coatings for wear, friction, and all these kind of things. So, coating is the way of the life, and it is required to protect a material or to give it durability. But then what is meant by smart coating? The meaning of smart coating is that which tries to do a function in a very specific manner and in a very perfect manner. That is what the definition comes into that. And one can just enumerate various kinds of things: self-healing, self-cleaning, conductive, corrosion sensing, light sensing, photocatalytic, and some of the examples which you are seeing right in the morning, some speakers have already covered. So what is self-cleaning? In simple sense, we mean self-cleaning is a process in which a drop of water, when it is exposed on a surface, it tries to collect all the, or it wipes out the dust or any other things which is there onto that. And this function is which is carried out without any kind of stimuli. The stimuli itself is that when a water drop is there, it moves and finally works onto that. Now, in order to such a drop should work, the surface should have some kind of basic requirement. And if you see many of these things, when a water droplet falls on a surface, the two important things which are required: surface is hydrophobic or it is hydrophilic. A hydrophobic surface is that where the water tries to occupy smallest place, and it doesn't like the surface, or it tries to conserve it in the smallest possible way. And hydrophilic is that in which the water droplet expands on the surface and covers as much as possible. So these are the two basic requirements, and everybody understands the lotus effect is one of the finest example. Why a lotus leaf looks very, very clean is mainly because when a water drop falls on that, it simply drags or walks onto that and cleans any kind of a dust into that. And that's why early morning, if you see many of these leaves, they are very clean because the condensation in the midnight cleans it and works into that. But if you go into detail of this whole process, then you will find that the two things which are working very nicely to make this happen. One is that there is an inherent wax coating. And this wax coating is making this surface saturated. And this saturation is the most important requirement for a hydrophobic nature. And second thing is that if you go into details of that and measure its surface roughness, then you find that the surface roughness, it has a specific surface roughness at which the drop tries to slide and it has that kind of a motion. So a combination of that really makes the self-cleaning process to happen. And in quantitative, what is the quantitative definition of hydrophobicity? The quantitative definition comes from the two things, combination of two things, the surface roughness, surface saturation, or the surface having low surface energy, which is synonym to the saturation, and specific surface roughness. If you combine these two, if they have a good combination of that, you can get a hydrophobic surface. And quantitatively, we say that and how to measure hydrophobicity? You measure the drop, the angle which the drop makes with the surface. If this angle is less than 90, we can say hydrophilic. If it is more than 90, it is hydrophobic. And if it is more than 150, it is superhydrophobic. Now, this is the example of a natural surface. Now, can we make any surface hydrophobic or hydrophilic? I think that is one which is the cause on which we started working onto that. Now, if you think from the point of view of lotus leaf model, then the steps are very much clear. You make a surface saturated and then try to create some kind of a roughness, and it will try to give you that kind of thing. And this is how one can create, in general, theoretically you can say that you can create any surface hydrophobic by this kind of process into that. Now, again, when we see in nature, you see in your homes, we have various kinds of, cooking pans. And if you just see the analysis of some of these coatings which are there, most of these coatings are fluoro-based coatings. And again, if you, any kind of a surface, if you see, to a greater extent, you find that fluorine is one of the important element into that. So what is the importance of that? Because fluorine is one of the elements which forms very strong bond. So when it forms bond with a polymer material like hydrocarbon, it tries to saturate the surface in such a big manner. That is one way to make the surface saturation into that. So that's why most of the fluorine-based material you will see, they are saturated and they don't like even oil or even water onto them. And second important thing is that how to create a proper surface roughness. Now the surface roughness story can be in two ways. One is that you can already create a suitable surface roughness before applying this kind of a coating, or you can create surface roughness after that, and that is what the nanotechnology has given us a very new roots for that. And by treating it with certain nanoparticles, you can create so-called the nano surface range surface roughness. And there are other methods which we have also tried, non-fluoro approach, because many people think fluoro approach is toxic, so it cannot be used for water and other application. So we have also tried non-fluoro approach. There's another approach which is quite well-known, photocatalytic effect of titanium dioxide. Here, the UV light tries to create radicals when it is interactive with titanium dioxide. And these radicals then, interact with the dust and other kind of things, discharge it, and it moves in that fashion. And the another fantastic technique which we have used is the functionalization of several pigments. Titanium dioxide is one pigment which is the important part of paints. And that's why you see many of the paint systems in which titanium dioxide is there, they are hydrophilic. And the reason for that thing is that the titanium dioxide, moment it comes in approach to any kind of moisture, it forms OH groups around it. So functionalization means that before you add titanium dioxide in a paint system, you try to close all its OH groups by some kind of interacting with some kind of polymers. And if you use such kind of thing, these pigments automatically becomes super hydrophobic, and when you add them in paint coating, they still show super hydrophobicness. And that is, these are the three technologies where I have got 3 PhD students in all of these. Now, what is inorganic-organic hybrids? Now, basically, as I told you, I'm talking about paint coating. And in paint coating, one of the most important ingredient of the paint coating is resin. And resin is an organic molecule. And organic molecules do not dissolve in water. So how to make them dissolve in the water? There are only 2 ways. One is that you can take some of the resins, convert them into a suitable salt or any kind of hydro dissolving material, or the other technique is sol gel technique. And what is this sol gel technique? In sol gel technique, we have the main important thing is the silanes. And these silanes are nothing but tetramethoxy or tetraethoxy things. And when these silanes are put in the water, one of these OHCH3 hydrolyzes and you get OH group. And now if you take any kind of organic resin which has at least one OH group in its chain, they react together and condensation reaction occurs and you get an inorganic-organic hybrid. And to see the nomenclature of that, in general, a inorganic-organic hybrid is indicated by this thing, where X can be any of the methoxy or ethoxy group. You know, TOS or TOMEs are very well known. And the R can be, in general, any kind of material, alkyl, aryl, organometallic, or any kind of things into that. And these are some of the examples which are available, things which are available in the market. And one of the simplest way to convert a silica molecule into a strong molecule is that you just take a silane and try to react with that. It becomes a siloxane chain. And siloxane chains are one of the very strongest one. And this is just an example that if you take one kind of a silane and try to condensation reaction with that, you create a molecule which gives a very strong and specific properties. Now, what I'm trying to say is that one of the most important property of the inorganic-organic hybrid is that they have the properties of both organic material as well as inorganic material. The advantage which is coming here is from the inorganic material. And what is that? If you take any kind of a silane, when it is applied on a metal surface, it forms a strong chemical bond. And it is a strong chemical bond which is changing the properties. See, in general, organic coatings have a mechanical bond, which means that this mechanical bond is very weak. And as a result of this, their temperature capability is only 80 degree to 110 degree or so. But if you take any kind of a silane, inorganic-organic hybrid coatings, they can be raised to a temperature of around 450 to 500 degrees centigrade. That is how the siloxane coatings are superior compared to that. So in our lab, we have worked with various kinds of inorganic-organic hybrids. And you can see right from epoxy, polyester base, alkyd base, and all these kind of things. And if I summarize the results of that, in general, I can say that all these siloxane-based coatings were much superior to that of the organic-based coatings. First, in terms of the corrosion resistance. Second, in terms of mechanical properties. And third, in terms of the UV properties itself. So all these properties are improved to a greater extent. And if I just show the results of epoxy-based thing, you can see that how the surface looks to be, and many of these, things are nano range, polymers. You can see the SCM picture of that, and if you see in the AFM of that, the roughness is of that. The only bad property of that is, I will not say bad, but one of the properties of that thing is they are hydrophilic. You see, the contact angle is around 75 degrees. Now, we had got a challenge some time ago that how can you convert this coating into hydrophobic coating? And that is how the whole research started. And then we thought of two approaches. The first approach, exactly the same way we thought, that try to treat this kind of things with a fluoro kind of a silane and make it the so-called saturated on the surface, the first requirement of Wenzel model. And secondly, create either a physical surface finish on the surface or by change the surface roughness by addition of nanoparticles. So in the fluoro approach, what we did, we just saw some of the silanes available in the market and also some of the commercial products available in the market. We just took that and tried to mix them. And this is how the whole scheme is there. This is the first step of hydrolysis. This is the second step of cross-linking. And after this coating is made, you treat it with a fluoro-based things, and you get a coating which has a strong CF3 bond. And because of this CF3 bond, you get so-called the saturated surface or a surface of very low energy. And this surface, now when you put a drop of water, this is an aluminum surface coated by this coating, and you can see how the water drops look into that. Now, and again, what is the effect of the fluoro group? So we tried various fluoro groups. This fluoro group which has 3 fluorine atoms, this one which has 17 fluorine atoms, this one has fluorine and chlorine atoms, and this has 6 fluorine atoms. So we found that in general, the fluorine compounds, they give a sudden range change to the hydrophobicity, and the effect of so many fluorine atoms is not very different, but one has to choose what is good for them. And the most important part of that, it is not that you just take any amount of these fluorine things and put into that. The result shows that if you add very small amount of that, then you get some improvement, but the maximum improvement comes when it is in optimum concentration. And if the concentration crosses, again the properties go bad. And this was the very important part of this thing, and this works as a very nice principle in nanotechnology. And then what are the changes which are occurring into that? The changes which are occurring onto the surface roughness and other kind of things. And what we found that out of these three, this iron sol was showing the best thing and perhaps a suitable roughness which was giving that effect. And this is the same picture for the AFM picture, 2-dimensional picture and 3-dimensional pictures, which gives you suitable roughness, which is perhaps responsible for creating hydrophobicity. Now, as I told you, the role of optimum concentration is very important. So when the concentration is optimum, then you find that the surface roughness or distribution of the fluorine particle is very uniform, and they are usually spherical in nature. And by Raman, we found that many of these things are still pure. But the moment the concentration is high, you find that these spherical particles or roughness get obliterated or becomes oval-shaped thing, and they also become reacting with something else, and you get impure things rather than that. And we also found that at this optimum concentration, you also have excellent corrosion resistance, excellent mechanical properties, and UV properties and things like that. And that establishes the thing that optimum concentration is most important, and this is one of the most important part of nanotechnology that you have to really work on to achieve that optimum concentration. Now we have already achieved the saturation of the surface with a contact angle of around 115, but we want to achieve 127 or 135 or so. So what is the next step? We thought now we should look into the effect of nanoparticle addition. So we add just simple nano zinc oxide with a particle size of 20 to 30 to 40 nanometer. And this is how the nano zinc particle size is looked into that. And this is how the nano zinc is trying to, catch the OH group and creates the hydrophobic surface onto that. And again, we studied the effect of nano zinc concentration, and we found around 2% of concentration gives the maximum contact angle. But this nano zinc oxide was not giving us a very good sliding angle. And sliding angle is still 65 degree, which is quite large, and this cannot give the self-cleaning effect to a very good thing. Then we tried silica particles, and this is now, you see how silica particles distribute to that. These are their size, and this is the total surface area. And in this case, you can see the change of hydrophobicity from here to here is basically the saturation of hydrocarbon particles. And again, here we studied the concentration of that, and we found that we could achieve 118 degree, but 20 degree less sliding angle. This was very good from the point of view of cleaning coating. Then what we did that we now try to do the functionalization of silica particles so that we can bind all the OH group in the silica particle as much as possible. So we used this dichlorodimethyl modification of silica, and we achieved very small particle size, but a contact angle of 122, but the sliding angle of as low as 35 degrees centigrade, 35 degree. And then we further modified, use another functionalizing agent, and there we find that the same thing happened. This particle size reduced even lower, and if you see the contact angle increases 125, and the sliding angle came down to 25. And this was a systematic thing, and if you see the comparison of all these four things into that, one finds that HMDZ polymer gave a average contact angle of 125 and average sliding angle of 25. And this is how, if you see into detail, what is really happening, what these nanoparticles are doing. So if you see, this is how these, for example, this is the effect of nano zinc oxide. You create a surface roughness which is best in the case of 2 weight%. Now we find that this nano zinc surface roughness over the fluorine surface, that creates a dual surface roughness, which is basically responsible for the self-cleaning effect or better sliding angle part of that. Same thing we did with the DDS thing. You can see very nice things here, and that gives the benefit of that. Now it is a comparison of all the four together, but you find that the best result comes when when you have HDM nanosilica particles here. I think this thing is just moved from here. So today, if you have to explain the effect of nanoparticles, how you can explain? Until and unless you have an optimum distribution of nanoparticles, which is shown in this fashion, what is called continuum theory, which means that if there is a nanoparticle like this here, it has effect up to a particular range. Beyond this point, like for example, beyond this point, its effect will not be there. Which means that if I have less number of particles than what is required, then I will have this kind of a distribution, and I will not get the optimum properties. If I have more, then the particle overlap, agglomerate, and the effect is finished. And that's exactly we saw in that Raman spectroscopy, that not only they agglomerate, they even react and create something else on the surface which is not good. So which means that the optimum distribution of this thing is very, very important. And this also defines how the particle should be distributed nicely into that. And when you have an axis of this thing, this kind of a situation occurs, which doesn't give you the best result. In order to confirm this, we again carried out detailed AFM studies where we studied the two-dimensional things, tried to find out how the particle distributed, And then we took the three-dimensional part and measured their surface roughnesses. And we found that a surface roughness is around 80 to 95 gives a very nice sliding angle. And what is the reason for that? This we did by calculating the F. What is F? F is nothing but the fraction of this water molecule which makes contact with the surface. So when we calculated this F, again we found that when the F is minimum when a optimum concentration is there and also the proper surface roughness is there. And this can be very nicely shown by the so-called Wenzel theory. That Wenzel theory says that when your surface roughness is small, the water droplet just gets entangled to this roughness and it doesn't move. It is hydrophobic, but it is not having any moving capability. But if you create a surface roughness by which you make the contact of this thing very less, in that case, the liquid droplet is able to move very less. This also can be interpreted that as the surface roughness is more, the bond between, which are the hydrogen bond, their effect reduces and the molecule moves in a much faster way. And this is exactly we have just shown. We calculated the work function of each of these particles with the substrate right from Wenzel state to the complete Cassie-Baxter state where the particle is moving into that. And this is exactly I wanted to show the dual thing. This was the surface roughness when we had the fluorine thing, and over this we have this fine surface roughness which gives you the sliding angle in a best possible way. And now this is the result of that. One of the most important result of this thing is that one particular formulation can give me superhydrophobicity on cardboard, on wood, on cardboard, fabric, glass, concrete, and even paper. And I just want to show you this whole thing in a slightly. So the left side is uncoated surface. I can move it faster. Oh, sorry. You can reduce this light, then they will be good. So this is the cardboard. This you see newspaper, normal paper. So the normal paper, you see the water almost, almost destroy this paper. But now you see here, doesn't even touch. So you can make currency which will not be affected by sweat. Fabric, I think this is one of the biggest advantage of the fabric is to make very sophisticated furnitures where very sophisticated fabrics are used, and they just get damaged by some drop of coffee stain or even red wine stain, or kids drop Coca-Cola onto that. So if this kind of a coating is put on that, you can just create a very nice surface which will not be affected by that. Yeah, last one I am showing is the concrete, all our walls. So when you just put a normal concrete and a normal cemented paint, you have this kind of a situation, and the wall gets damaged because of that. But if you put this coating, the water doesn't even touch it. Now you see here, one of the drawback of this whole thing was that if you see on the glass is, when you use this fluoro-based coating, it has become translucent. Now if you want to use glass thing on on this coating on the glass, then even solar panel or other kind of things, then there is a problem of translucency. So what we did in that case, we used the other technique, non-fluoro approach. In non-fluoro approach, we just took the same kind of a thing and tried to react it with some kind of a polymers where all these OH groups just get banned, just get fixed, and you get the saturation into that. But and in the initial stages, what we did was that we added silica particles from outside. So when we did that, the biggest problem was that it was not fully transparent. Then we tried to find out a technique to create in situ silica particles by the use of this thing. So we just tried to react it with this directly, and then tried to add this in the end, where it tries to react and creates nanosilica particle inside. And that gave a fantastic things into that and gave a very good superhydrophobic coating into that, and also clear. So this is here we have found the gel time of this thing with various combinations. Then we find out what is the thickness of that, which comes with various coating method, brush, dip, drop, spray, or spin. Then we found that what is the contact angle we are getting into that. And then we carried out, of course, to confirm all these things. Then we found out how the silica particle is distributed. And we found that this role of silica particle is very, very decisive in this case. If you just take the cold coating, the silica particle is available on the surface in this fashion. But if you do the heat treatment and other kind of things, it just vanishes and goes down at the back. And it helps in creating another thing, coating, which we found it was a requirement of this contact lenses, where you want to create an anti-glare coating. So you create a coating of two layers, where two layers of slightly different refractive index. And by this, we could create that kind of a thing. Now, the only problem was that when we used this kind of thing with the brush method, the situation was like this, but the coating thickness is really not enough. Then we tried to do the whole thing with the so-called spin coating. And the results were excellent. So in that, we found there was not much change into that, except that we could find that the silica particles, which were very tiny silica particles available on the surface, with heat treatment, they go at the back and they make a very clear thing. And with a very sophisticated experiment, we could measure the thickness of this coating in a very nice manner, around 100 nanometer or so. And this is how the surface roughness looks like that. And we also find out the toughability of these coatings, because for contact lenses, they also want the coating should be tough, it should not get scratched. So very good nano indentation results were coming into that. And these are the final results. The most important part was here, whether the coating is transparent or not. So this is exactly, you can see, the blue one is the glass, and this is the heat-treated coating, which is showing exactly same kind of transparency as the original glass. And that is what the most important part was there. And these are the reflectivity of three different coating. Original coating before heat treatment and after heat treatment. So there is a slight loss in the refractive index, which creates a very nice coating over that. And to use this coating for solar panels, we carry out tests on the standard solar panels and try to measure what is the kind of voltage drop changes when you apply the coating and without that. And the result is almost very good into that. So we are now at stage where we have to convert these things into the so-called commercial model from so-called the lab model. So I just finish it here. Again, I will find this will not come. I will. Just to show that how the self-cleaning process works. And these are transparencies of that. So this is the thing with glass where no coating has been applied, and this is where the coating has been applied. You can see how nicely it is removing this thing, and at the same time, the transparency of this coating is excellent. So these are the various applications which we can look into that. Multi-story buildings, 100 stories or things like that, where the all glass surface is there. Cleaning them by conventional method is not really good. And this is how the solar panels, after some time, they become like that. And when they become like that, they start losing their absorbability. So would you like to use broom and soap water to clean them? Or will you like to use this so-called self-cleaning coatings to put onto that? These are the important things in the beautiful drawing rooms of rich people and in many places. And nobody wants to like to have a stain from coffee or a stain from Coca-Cola. So for such kind of things, you can use this kind of thing. So now this is just a slide which just shows only for, this is from the nano markets data, which shows that by 2019, the demand for the window coating itself, glass coating itself, will be around 1,400 million. So that is what the requirement of this thing is there. So I want to just justify that subjects like this which create this kind of smart coatings are really of great importance, and research work which shows this effect, which is already well known, but to understand the results and how it can be used for a particular application, that is what is the most important part of that. And now we are in the process of converting it to a commercial application. Thank you very much for your kind attention. Sorry, team chairman, I have taken 7 minutes to go. Nobody stopped me, so I took 7 minutes.
Yeah, thank you very much, sir. Appreciate that.
Any questions?
Does the coating impart any oleophobicity?
We have so far not seen any kind of oil things onto that, but the literature shows that if your hydrophobicity is super hydrophobicity, the oil can very well be repelled from that.
And how do you coat the paper? How do you coat the paper? Just paint it on?
Normal spray method. Most of the things we have done by the normal spray method. The spin coating we use only for this this lenses, because here what we are looking at very, very thin coating. So you can see the coating thickness here is of the order of 100 nanometer or so, compared to several microns in the case of other things.
Thank you very much, sir. One last question, then we need to move on. We're already over time.
Some of these coatings are already commercially available. And one of the challenges with the commercially available coatings is the wear resistance. So have you done any kind of taper testing to show these could be used for industrial applications?
Actually, this coating which we are there, we are just selling it to the Titan company who makes these pipes. And their requirement is hydrophobicity, anti-glare, and anti-scratch resistance. So we, by controlling the silicon oxide concentration, we control the scratch resistance also. By heat treatment, we control their, different kind of a coating onto that. And the third requirement was the anti-fog, which we couldn't mix with this. So we are giving them an anti-fog coating separately, and this coating with 3 things into that. So that is not but if you want on a other surface where transparency is not the requirement, we can give you a very strong anti-scratch coating also along with the